Okay. Suppose that 43% of registered voters in Arizona are Democrats. That gives us P, the true proportion is 0.43. Okay. Now we want to know what is the probability that there will be less than 30% Democrats in a random sample of size 50. To start the problem, we are going to define P hat. P hat is dealing with our sample. This is the true proportion that we assume is true. Okay, so assuming this is true, we want to find the probability that P hat is less than 30%. How are you going to write 30% as a proportion? 0.3. Okay, we usually just write it as a decimal. So you could write 30% if you wanted to. You could write 30 over 100. Okay, you could write 3 over 10. Usually we just use decimals. Don't you like decimals better? Okay, so we're trying to find this probability, the probability that in my sample I get fewer than 30% of the people are Democrats, knowing that this is true. This is the true proportion. Okay, so we define P hat is the sample proportion of Democrats, in other words, the number of Democrats in our sample of size 50. We must always check our conditions before we proceed any further. So we're checking to see, is it from a random sample of a population of interest? Well, yeah, it is a random sample. We're assuming that just say random sample from a population of interest. You don't need to write a paragraph. Okay? If they don't say random sample, say we assume it's a random sample. That's what you do. Okay? Second thing from up here. Okay, B from up above, it says the sample is less than 10% of the population. That basically this is the independence condition. Independence condition. Is it independent? Well, if you're asking people from a state, every time you remove a person, it's actually not independent because you're lowering the pool of people to ask from. But from back in the last chapter, we talked about if you ask only less than 10% of the population, it's okay. So you might know the 10% condition, the independence condition. There's the random condition, the independence condition. So we assume whatever our sample size is. What's our sample size? 50 is less than 10% of all registered voters. Registered voters in Arizona. Try to always talk a little bit in the context of the problem. The context of the problem means just referring to, we're talking about voters in Arizona. We're talking about doctors working in the hospital, all the hospitals in Texas. You know, whatever you're talking about, try to refer to it at least once in checking your conditions. Okay, the third condition we have to check is that N times P and N times Q are both greater than 10. They can be equal to 10. All right, so now we've got to figure, well, what's N in my problem? N is 50, and P. Now, P is the true proportion, 0.43. Your probability proportion, the only time you don't even use this 0.3 except for right there. That's the only place you're going to use it. The true proportion is what you're going to use because we're assuming the true proportion is true. Knowing this is true, what's the chances we get this happen? So, and that would make Q equal to 0.57? Yes? Okay. So 50 times 0.43 and 50 times 0.57. What do you get? 21.5 and 28.5. So both are greater than 10, right? Both greater than 10. All right, so now we checked our conditions. All right, so now, and this last condition is called the large sample size condition. Large sample size condition. And they're actually all named, well, they're not really named up above, but we gave them names now. All right, so now we can actually look at our problem. Now we can look at our probability question. What is the probability that P hat is greater than 0.3? Okay, well, P hat, now that we've checked all our conditions, we can actually, to find this probability, use a normal model. Okay, So what we're going to do to change this to normal, so now what we're going to do is we're going to change p hat to normal. Well, not really, yeah, we're going to change it to normal. And the way you change it to normal, you use the formulas from up above. P and the square root of PQ divided by N. So P is what? 0.43. And then the square root of 0.43 times 0.57 divided by what? 50. Okay, I don't really even have to figure that out. I can just leave it like that. But I'm sure you want to get a decimal, so it's approximately normal. P hat is approximately normal. 0.43 is the mean. The standard deviation, what's the square root of 0.43 times 0.57 divided by 50? 0.07, okay. All right, so now, see, I ran out of room. I'm gonna finish this right down here. Okay, so now we can draw our normal model. What goes in the middle? 0.43, and up one standard deviation puts us at what? 0.50, and then 0.57, and then how am I getting from here to here? What am I doing? Magic? Alexis is doing magic tricks. You're adding the standard deviation. That's what you're doing. Okay, so what's down here? 0.36, and then 0.29, and then 0.22. So here is our normal distribution for p hat. This is the sample proportion of Democrats. Okay, so we would like to now know this probability. The probability that this is p hat down here. All of this whole thing on the bottom, this is p hat. The probability that p hat is less than 0.30. Okay, now, have we done problems like this before? The only difference is instead of having p hat, we had x. Okay, now we just have p hat. So 0.30 is like right here. There's 0.30. And less than that is shaded over here. But haven't we changed p hat to normal? So now can we use NCDF? So now we're going to use NCDF, normal CDF, and then you type in your lower bound. We call it lower bound. It's what's on the left of your graph, and then the right of your graph, and then the mean and the standard deviation that we just calculated from right up here, from right there. So what is on the lower bound down here? Negative infinity, negative 9999999. Okay, so negative 999, not point, just need a bunch of nines. And then what is the upper bound? 0.30. What was your mean? 0.43, and the standard deviation? 0.07. So you've got normal, CDF, and you've done that, and what do you get? 0.0316. Okay, that means 3% of the time you're going to get fewer than 30% Democrats, knowing that there are 43% Democrats in Arizona. Okay, and this is how a lot of your problems are going to go. So we're just probably going to look at another problem now. Okay. So basically this is the same, we're dealing with the same thing. So we've got the same p hat is approximately normal with the standard deviation of 0.43 and or a mean of 0.43 and a standard deviation of 0.07. So we've already got that, and I'm just recopying the picture. Okay, so here's my normal curves, because now I'm asked about exactly the same thing, so I don't need to reinvent the wheel. I don't need to redo everything I did. I already checked my conditions. I can answer all kinds of questions regarding this because I changed it to normal. So now I want to know, what is the probability that the sample proportion will be within 5.05, 5% of the true proportion? Okay, so isn't this the true proportion actually? Okay, this whole thing is a graph of p hat here changed to normal, okay? But the true proportion actually is the mean. Okay, we use the true proportion as the mean. So 5%, 0.05 of that, don't you just subtract 0.05 and add 0.05? Doesn't that give you a range? Okay, what's 5 above 0.43? 0.05 above 0.43? 0.48. So we're looking, so what is the probability that p hat is between, sorry, I'm going to write this, p hat is between, okay, the upper bound is 0.48, and what's the lower? 0.38. So we're actually asking, what is the probability that p hat is between 0.38 and 0.48? So here's what I do. Notice I redefined, I wrote the definition, p hat is normal. I drew the picture, now I'm going to draw, shade in. I'm looking for this section right in here. This is why the normal model is so wonderful. The binomial problems that asked you to go in between, they were kind of a mess, weren't they? You had to subtract things or, you know, do 1 minus things. It was a mess. The normal model is nice because the normal model, now you can just do normal, CDF, lower, upper, mean, and standard deviation. That's all you type in. So what is the lower bound of this shaded region? 0.38. And then the upper bound, 0.48. What was the mean of our distribution? 0.43. And the standard deviation? 0.07. So you type that in and you tell me, that'll give you your answer. This should seem familiar. The only thing different is you start with proportions and you have to change them to normal. Okay, what do you get? 0.5249. That seems about right because isn't that pretty close to taking up 1 standard deviation above and below? Pretty close. It's a little short, so that would be 68%. So it makes sense that we're less than 68%. Okay, so now the next question is, how can we make this probability bigger? Okay, how can we make this probability bigger? What is the probability that the sample proportion will be within 5% of the true proportion? In other words, this is actually a very important question up here that we ask. Being within 5% of a true value, isn't the 5% like the error? The 0.05 is 5% is the error. Basically, we said, how can we get our sample, our p hat, to be the same or really close to the true? How can we get our sample to be closer to the true value? That's what we're asking. So the 5% from up here, a range of 5 is like our error. So how can we make that error smaller? Okay, any ideas? What? Ask, exactly. Ask more people. Okay, now, how does that equate to our variables? Or what will make n bigger? Make n bigger. Larger sample size. Okay. So if we just take a look at a couple of things, what if n was 100? What if n was 500? Okay, if n was 100, here's what would happen. I'm just going to do this real fast. If n was 100, p hat would be different. Okay, both of these are going to work. N times p and n times q are going to be greater than 10. All the conditions will work. But what was n before? 50. And we had that n was 50, and then we got that p hat was normal 0.43 comma 0.07. If n is 100, p hat is normal 0.43 comma, well, now this time take the square root, the square root of 0.43 times 0.57 divided by 100, and hit, why did I do that? The new standard deviation is 0.07.